Good afternoon, Prof. NTA. Today, we Group 17 will present on our project 2. We did all of the tasks, but we will further explain on some of the features that we specifically implemented in this task. For the trajectory generation, we need to define the finite state machine that can be defined in this diagram. It first starts at the takeoff state, then when it reaches the required height, it will change its state to start. Every time the hector is near the initial position and its state is start, it will check whether the turtle has reached its final goal or not. If not, it will maneuver itself to the turtle, then to the goal position, and then back to the initial position. However, if the turtle has reached its goal, it will directly command the hector to land. To generate an intermediate target, it will first find the estimated time to the final goal in each state, and if it is greater than the look-ahead time which has been predetermined, it will look for an intermediate target that has a distance of v times t, which are both variables that has been predetermined. The intermediate target should also lie between the direction from the current position and the final goal. However, if the estimated time to the final goal is less than the look-ahead time of the hector, it will directly set the final goal as the intermediate target. Next, we will input the current position of the hector, the position of the intermediate target, and the position of the final goal in the respective order in a vector, and publish it to the message trajectory topic, and the intermediate target's location will also be published to the message target topic. The first problem that I encountered was that I miscalculated the intermediate target's position, in which I only took account of the distance to the intermediate target without adding it to the hector's current position. Second, the yaw has caused the hector to drift a lot and create a lot of miscalculation on the hector's pose. Hence, we decided to not let the robot rotate throughout the course. Third, I initially used a vector of intermediate targets, but this has made the targeting system static, as it's wait for the robot to reach for the current target before updating to the next one. We found out that having only one intermediate target will make the targeting system more dynamic and computationally lighter.
Next, PID motion controller is implemented for each axis with X and Y using linear gain and Z using Z gain. In this controller, saturation function is also implemented to mitigate some issues. Additionally, your velocity in this case is also engaged when rotate is on. To collect data for observation on the PID result of its axis, we take a look at target, position, velocity, and corrections using these commands. Upon running these commands, we get these findings. These are the graphs generated from the data extracted and processed through MATLAB. These graphs show what's going on each axis from target, position, velocity, and correction. There are some slight differences and some fluctuation occur for each axis, but in general, it follows the target well enough with this configuration in the left. There were some problems, namely unsaturated PID, which led to failure in maintaining velocity, and this is easily solved by applying saturation function, and unstable PID, which led to unstable movement of the hector. This is solved by tuning the PI, P, and D part, proportion, and derivative part.
Next, the extended thermal filter can be divided into two parts, the state prediction and state correction. For the prediction, we are using the IMU because of its high accuracy and high frequency updates. For the correction, we are using the GPS, magnetometer, and sonar. So before we discuss our findings, here's the procedure on how we do the data collection. To find the variance, we first set the hector into idle mode, and next we run this raw topic echo command so that we can get the data in a TXT file. Then we transfer it to MATLAB and use the bar-a command of MATLAB to get the variance of the data. For comparing with the ground truth, we publish 5 new messages to get the data we need. Then we do a Rosberg report. After we get the Rosberg of one cycle of moving the hector, we do a raw topic echo and do the file transfer to MATLAB by default. Next, we will discuss our findings. For GPS, we can see that X and Z deviates not more than 0.5 in value. Thus, we may say that the GPS has an uncertainty value of plus minus 0.5. GPS is not subjected to drifts like IMU because it has absolute position. For the magnetometer, it has very small variance and can be seen from the graph on your right side that the ground truth and the plot is really similar. This means that it is a reliable sensor, but only in simulation, because in the real world, it is very sensitive to the environment. Therefore, it is needed to isolate it from magnet-inducing motors. For sonar, the output seems similar in some parts, like the first part and the end parts, and the variance is really small, meaning that this should have been a reliable sensor. However, as you can see from the graph, there are fluctuations, which is caused from the hector going over the turtle and the box's information. So it is needed to implement a special function, but we didn't manage to do so.
Next, when investigating IMU, we found out that the mean and the variance of linear acceleration X, Y, and Z, and angular Z as such. From there, we suspect bias happened even when negating it. Upon consultation online, it might be related to velocity random walk. In the end, we continued using our best variance configuration so far, as shown this, upon multiple tunings.